In this unit, we'll be taking a look at the functional group aldehydes and ketones. They both share a similarity, which they feature this carbonyl, which is a carbon double bonded to an oxygen, which is not in itself a functional group. It's just an arrangement of a carbon and oxygen together. And then depending upon what you flank that sp2 hybridized carbon with, will determine whether or not you have an aldehyde and ketone. And so an aldehyde would feature some type of carbon residue attached to that carbonyl and also a hydrogen, and then a ketone would have two different carbon residues. When we take a look at this functional group, one thing that I want to do is take a look at how do we prepare this functional group, so the synthesis of that functional group, what reactions produce those ketones and aldehydes. And then I also want to be able to take a look at what types of reactions do aldehydes and ketones undergo. And so let's just kind of split this piece of paper up into two different halves here and take a look at how can we prepare aldehydes and ketones. Are there any reactions that we've been introduced to in the past that we can use to prepare aldehydes and ketones? And one of the methods that we'll take a more in-depth look at is converting alcohols, the ROH functional group, into some type of aldehyde and ketone. And when we go over those notes, just as a brief overview, we'll be talking about how we can convert a primary alcohol into an aldehyde, and then also how we could take a secondary alcohol and convert that into a ketone. Another method that we may have studied before is the conversion of an alkene, so a carbon-carbon double bond, into a aldehyde or ketone, and this process is a process called ozonolysis. And when we take a more in-depth look at ozonolysis of alkenes, we'll be able to predict and generate products based on our starting alkene. And depending upon what alkene we start with, we should be able to generate either aldehydes or ketones. And as an overview of this idea, and something we'll take a look at more specifically and mechanistically, is the conversion of something like ethene into aldehydes. And in this case, what you'll find is that an ethene molecule is converted into two separate aldehydes through this ozonolysis process. But if we take a monosubstituted alkene, so something where just one of those hydrogens on ethene, so kind of in the example that I have written above, if you were to subject a monosubstituted alkene to some type of ozonolysis process or conditions, you would generate two aldehydes from that as well. And just kind of continue with this overview, if we were to begin with a disubstituted alkene, so in this case, taking a carbon-carbon double bond and replacing two of those hydrogens with some type of carbon residue or other substituent. If we had a cis-trans type isomer of that disubstituted alkene, we would again generate two different aldehyde molecules. And we'll look at this definition a little more closely, but if you have a geminal alkene, and that's where those two R groups are both on the same carbon, so same side of that alkene, you'll actually generate an aldehyde and a ketone from that. And we'll take a look at how that happens mechanistically, and it's not something you'll need to memorize, it's something you'll be able to derive. Let's take this one step further then with our overview. A trisubstituted alkene. We could also place a trisubstituted alkene under some type of ozonolysis conditions. And in that case, you will generate one aldehyde and one ketone as products of this reaction. And finally, to round this overview out, if we were to replace all four of those hydrogens on an ethene molecule with four other substituents, four other carbon residues, you would then, if placed under some ozonolysis conditions, you would produce two different ketone molecules, or 2 ketone molecules, depending upon what you have substituted to that alkene. Of course, there will be intramolecular versions of these as well, but this is an overview for what you're most likely to encounter when you look at these reactions. And then the last thing that we'll take a look at with our videos is the conversion of alkynes, and specifically we'll be looking here at a terminal alkyne that we should be able to produce aldehydes and ketones from that reaction as well. This is a hydration reaction, or addition of water reaction to an alkyne. And there are really 3 different definitions of alkynes, or 2 rather. There's a terminal alkyne, and then there's an internal alkyne. And depending upon conditions that we'll cover in that video, we will be able to effectively have Markovnikov addition of water to a terminal alkyne to generate a ketone, or we'll be able to take a terminal alkyne under different conditions and have anti-Markovnikov addition of water to generate an aldehyde. And then finally, rather, at the end of that video, we'll talk about what happens with internal alkynes and the fact that they generate ketones as products. And so we'll look at that mechanistically as well. And so just trying to provide a brief overview of the things that we'll encounter. And again, when we look at these functional groups in these videos, we're going to break this down into, once we have a set functional group, how do we prepare that functional group, and then how does that functional group react? And so when we take a look with these videos about the types of reactions that aldehydes and ketones will undergo, well, those can be split up into 2 separate categories. And if you remember your ethers and epoxide section, this is going to become, or epoxide specifically, this is going to become very familiar, because in the epoxides reactions, the types of reactions were really split into 2 different types. Either you would add acid first, or you would add your nucleophile first. And the same is going to be true with aldehydes and ketones. There is going to be a class of reactions where we're going to protonate or aldehyde or ketone first and generate some type of products. And the functional group names for these types of things are hydrates, acetals, cyclic acetals, thioacetals. Lots of fancy functional group names, but all of them share the same mechanism, and so there's not really a lot to memorize here. There's a mechanism to understand that we can rely on to derive these products as well. There's also another class of molecules that will react under acid-catalyzed addition conditions, and those are amine-bearing compounds, nitrogen, NH2-bearing molecules, and again, these will all follow the same mechanism as well. One would argue that the 2 subgroups that I've separated up there both share the same mechanism, but those will produce imines, enamines, oximes, and hydrozones as a result of reacting nitrogen-bearing compounds under acidic conditions to aldehydes and ketones. Well, if we're adding acid first and then adding our nucleophiles under acidic conditions, then the other type of reaction would be adding our nucleophiles first, independent of acid, and then acidulating our product, our alkoxide, our product in the end with acid. And those types of reactions, that is a subgroup, are reactions that produce alcohols and cyanohydrins. And again, those will share the same mechanism. And then finally, we'll take a look at alkenes, synthesizing alkenes through nucleophilic addition reactions, also known as the Wittig reaction.